Good morning, and today we are talking about real numbers, and this is the first lesson of CBSE 10th class mathematics. And as you are all familiar with this number system, uh, we have a natural number system and a set of natural numbers. We start from 1, 2, 3, 4, and so on. This is the set of natural numbers. Then we have a set of whole numbers, and we include 0 here. So 0 is a whole number but not a natural number. Then the next set we talk about is a set of integers where we denote it by z, and 0 is here. As you move to the right side, when you write positive integers, you also go to the left side on the number line, writing -1, -2, -3, and so on, and this extends this side to positive infinity. So you have negative infinity to positive infinity. There are so many integers actually, and between any two integers there are so many fractions. Okay, and those fractions and these integers together, we call them rational numbers. So when you say a rational number, and this set is represented by letter Q, and a rational number can be written in the form of P on Q. A rational number can be written in the form of P on Q. Okay, and there is a condition here that P and Q are integers, and Q is not equal to 0. Okay, so if you have in the form of integer by integer, you call it a rational number. And but denominator, you should never have 0. It is undefined. Division by 0 is undefined. Therefore, you shall never have a 0 in the denominator. Otherwise, rest any integer by integer is always a rational number. Let me tell you how this 4 is a rational number. 4 can be written as 4 by 1. So this is an integer, and it is also a rational number. Okay, it belongs to both the categories, rational number. Suppose you have a fraction like say 5.5. This 5.5 is the same as 11 on 2. So you have integer by integer form. So this is also a rational number. Okay, let us say you have a terminating decimal, say 0.3. So this is the same as 3/10, 3 on 10. So terminating decimal here can be written in the form of P on Q. So this is also a rational number. Sometimes it so happens there is a non-terminating decimal, but it's repeating. Non-terminating but repeating. Let me say I write 0.3 but bar upon 3. So this is continuing actually, 3, 3, 3, 3, and so on. It's non-terminating. So this is 1 on 3, if you can understand. So non-terminating but recurring, or non-terminating and repeating or recurring, both are same. Such decimal numbers can also be written in the form of P on Q, integer on integer, and these are also rational numbers. Okay, so the question obviously comes, when do we get irrational numbers? If it is not a recurring one, okay, non-recurring one, and non-terminating, it doesn't come to an end. Okay, you have to truncate it somewhere and you have to stop. Okay, so non-terminating and non-recurring, okay, numbers, we call them irrational numbers, like say root 2, root 3, pi, all such numbers we call them irrational numbers. Okay, and otherwise most of the numbers we come across, of course, they are rational numbers. We deal with many times rational numbers, but there are some irrational numbers which can't be written in the form of p on q. So see, if you can't get the square root as an integer, it should definitely be an irrational number. Say for example root 4. Okay, root over 4 is 2. So that's a rational number. Root over 9 is a 3 plus or minus 3. So it's an integer, like, the square roots are integers, 2 square roots you have got. But if you are not getting a perfect square root like that, which is an integer, all the time they end up as irrational numbers. So this is a little about real numbers, and specifically in this particular chapter, he is talking about a fundamental operation called division. Okay, so today we are talking about division and the properties of division and Euclidean division lemma and how we can determine the HCF of two numbers using an algorithm. So this is what we are supposed to do in this lesson of grade 10. So let me take now division as a property. Okay. My topic now is the division. We understand what division is all about, and we also try to find some important properties of this division. Okay, let us take an ordinary division as we find it. Say you have 13, a number. This is called a divisor. When this 13 is divided by 3, and 3 times 4 is 12, and this is 1, and you know the components of division and how they are related. This 13 is called divisor. 13 is a dividend, and this 3 is divisor, and this is quotient, and finally we end up with a remainder. So if you understand that these are the components of division, you should understand the relation between them. 3 times 4 equals 12, and add 1, and that is how you get this 13. Okay, 3 times 4, 12, and 1, and that gives you 13. Something very important you have to notice here, that this remainder can never be larger than this divisor, because like when some chocolates are being divided amongst some children, you can never have more than 3 left, because 3 children are taking the chocolates. There are some chocolates, everybody gets some chocolates, but how many remain can never be more than the number of students who are sharing, as simple as that. And obviously for that reason you should remember this remainder can never be larger than this divisor. Okay, as simple as that. But sometimes when some divisions, this can be 0. Okay, there is absolutely no problem. There's no chocolates remain there. Actually, they divide perfectly. Everybody gets a whole number and there are no chocolates left actually. So anyway, fine. Now let us take the same way here, the components of this division, and understand the relation between them. So divisor times quotient added to this remainder shall give you this dividend. So I write here dividend is equal to divisor times quotient, and this remainder is added actually, remainder. And if you generalize this one, I take a here and divided by b. There is absolutely no condition that a should be greater or a should be less, whatever it is, absolutely no problem, of course. In fact, this can be less also, in which case your quotient will be 0. Okay, anyway, fine. When this division is done, okay, you get some quotient, and some remainder here r. But something interesting here is that this can be 0. Okay, that's the condition. So b is not equal to 0. But a and b, of course, either of them can be greater than the other, and that doesn't make much of a difference there. But what is the relation here? If you follow the same principle as you are doing in this example, b times q plus r is our a. Okay, so here a and b, I take them from the set of integers. Okay, now let us write that a equals b times q plus r. Okay, you can even write a small remainder here, no small lowercase you can take. So now let us understand actually what all these variables mean to us. Okay, a is the dividend and b is the divisor, q is the quotient, and r is the remainder. This is how they have a relation, and this is a proven statement which doesn't, this can be used elsewhere. Okay, Euclid has given this relation between them in his book of elements number 7. So this is called a Euclidean lemma. Okay, Euclidean division lemma. So you should understand certain terms in mathematics, like we have an axiom, we have a postulate, we have a conjecture, we have a lemma, we have a theorem. Okay, so these are all the fundamentals. Of course, you should try to understand what they are. Say, for example, if you have an axiom somewhere, it is a basic fact which doesn't need any proof, and postulate means the same. Okay, similarly, here you are using a term called a lemma. It is a proven statement, and this is amenable, of course. You can use it elsewhere. Okay, so this is what we mean by Euclidean division lemma. But remember one thing here, what these variables can be. B can be 0. Okay, but a can be 0. There is no problem. I can divide 0 by some number. Okay, and there is no problem, of course. 0 times 5 is 0 and the remainder is 0. Of course, I can have the dividend can be 0. There is no problem there. I can have, say for example, if I take 12 and this is divided by 3, 3 times 4 equals 12. Remainder can be 0, because this is another option, of course. R can be 0, but R can be 0 or more than that. But the condition remains here is that when you are writing this remainder, this can be 0 or more than that, but it should be less than b. And therefore, a condition, of course, which has to be very religiously followed is r can be greater than or equal to 0, but it should be less than b. Remainder can be either 0 or more than that. But however, it doesn't exceed in any case more than this divisor. Remainder can never be more than the divisor. Remainder can be 0. Okay, if you take this division, you easily notice something. When this 12 is divided by this 3, as you got this remainder 0, this 3 is also called a factor. So the divisor becomes a factor. 3 is a factor of 12 because your remainder is 0. So this is what you should understand, Euclidean's division lemma. There are some interesting things, of course, that you have to notice when you talk this simple division. Say for example, I take some number a. Okay, and when I take some number a, I want to divide it by, let us say, 3. Now, my contention is not a very complicated one. There is some number, okay, some integer I have taken. So I have divided this number integer by 3. So I got something like, maybe some m, which is also an integer, and I get some, say, remainder r. Okay, so as I have told you that this r can never be more than this 3, what can that be? It can be 0, 1 or 2. That's it. It can be 3 or more than that. This remainder can never be more than that. Therefore, how do I write this A? A is equal to 3 times M plus R if I write. Okay, so what can this be? This A can be, okay, and it can be 3M plus 0. I don't mention that 0 here. It can be 3M plus 1. Okay, or it can be 3M plus 2. Okay, it won't go beyond. It can be 3M plus 3 because like it should never exceed this 3. And therefore, if you have any integer, no conditions here, any integer, it should be of one of these 3 forms actually. Like it can be something different. Exactly the same way, suppose you have some number, say P. Okay, and it can be expressed, suppose I divide it by divided by 5. It can be 5 times n, 0 is the remainder. It can be 5n plus 1 because when you are dividing it by 5, the remainder can be anywhere between 0 and 4. So it can be 5n plus 2, it can be 5n plus 3, and it stops here, 5n plus 4. It can't go anywhere more than that. So my point here is, when you are dividing any integer by 5, it should be in one of these forms. Okay, it can be in any other form. It can be a multiple of 5, a multiple of 5 leaving remainder 1, or at best it can be a multiple of 5 leaving a remainder 4. That's it. So you should understand any integer, okay, can be expressed in any of these 5 forms. If you any of these 3 forms. If you let us take, say for example, I just have say some Q. I just take some other letter S, and I am dividing this S by 2. Okay, when this S is divided by 2, there are only 2 cases. Either it leaves, say for example, multiple of 2, or it leaves a remainder 1. Any integer you have, when it's divided by 2, no remainder here, and there is 1 remainder. You can't have 2 as the remainder because you are dividing it by 2. And obviously, numbers which are multiples of 2, we call them even numbers. And numbers which leave a remainder 1, odd numbers. That's it. All the numbers are of only 2 categories, either multiple of 2 or numbers which leave a remainder 1 when divided by 2. That's it. So you should understand how you can express any integer you are given. Okay, let us try the last one. Suppose you are dividing a number by 7. There are 7 remainders possible. So it can be 7 multiple and 1 as remainder, 7 multiple and 2 as remainder, 3 as remainder, and 4 as remainder, and 5 as remainder, and the last one 6 as remainder. So when a number, any integer for that matter, is divided by 7, obviously there are 7 remainders possible. No remainder, 1, 2, 3, 4, 5, 6. So there are 7 ways a number can be written in any of these 7 forms. So that is what should be remembered here, of course. Okay, and now if you want to find out the HCF of 2 numbers, okay, we were doing some division method, and let us understand the algorithm of that. Okay, so when you have say 2 numbers, and if you want to determine the HCF of those 2 numbers, what can be done? Okay, now how do you find out, see, the HCF of 2 numbers? Let us do it first actually, and we'll take 2 numbers arbitrarily chosen, and let me take, say, 36 is one of my numbers, and 15 is another number, of course, I have chosen, arbitrarily chosen. If you want to find out, okay, the HCF of highest common factor, let us write down the factors of 36. 36 comes in 1 table, 2 table, 3 table, 4, 5 table it doesn't come, 6 table, of course, then 9, and 12 3 is 36, 12 table it comes, and then 18, and finally it comes in the same 36. These are the factors of 36. Now what are the factors of this 15? So 1 of course is a common factor of all. 3 times 5 of course is 15. 3 and 5 are factors, and of course the last 15 itself, the number itself. So when you have 15 and 36 this way, now identify the common factors. 1 is always there as common factor of both, and here you have 3 at both the places and nothing more. And therefore what is the highest of the common factors here is 3. Okay, 3 is a common factor of these two numbers, and at the same time of course there is no factor which is larger than that, and therefore here you write HCF is equal to, you are writing 3. Okay, this is to understand from the basic principles of like factorization and how we determine this HCF. Fine. This can be done in division method. That's what you did when you were in lower classes. 36 is divided by 15. 15 times 2, let us say 30, and 6. I haven't got a remainder 0. So the procedure I should continue. So how do I do that is, I take this 15 here, okay, and I continue doing my division. I just draw a line here. 6 times 2 is 12, now 3. Even now my remainder is not 0, okay, so I continue further. So this, I take this 6 here, and 3 times 2 is 6, 0 is the remainder. So I got 0 remainder, therefore this is my HCF. As simple as that. So this also you learnt, and this should be understood, okay, keeping in mind this Euclidean division lemma. Okay, and algorithm when you talk about, okay, it's a step-by-step procedure. Algorithm when you talk about, this is step-by-step procedure of problem solving. Step-by-step procedure of solving a problem, as that's called algorithm, step-by-step procedure of solving a problem. So we want to find out a procedure how we can find out the HCF of two numbers, and we are trying to generalize that. We are going to write this procedure there. Now algorithm is a term, of course, that is that comes from an Arab mathematician, Al-Khwarizmi. Okay, and in his honor, of course, he's an Arab mathematician, and we use this term algorithm, Al-Khwarizmi. Actually his name is Abu Jafar Ibn Musa Muhammad Al-Khwarizmi. Okay, if you can remember, it's good. In fact, otherwise, of course, not necessary. It's Al-Khwarizmi. Okay, and in his honor, of course, we use this algorithm. It's a step-by-step procedure. Now, my contention is very simple. Okay, and I take two numbers A and B, and my what I need to do is that I have to find out the HCF of those two numbers. How do I go about is, that I want to write the algorithm for that. So so let us begin taking two integers A and B, and let us see how we can do that. So I have A and B. These are the integers given to me. Okay, and I go with an assumption that A is larger than B. It's only an assumption. You can pick up whichever is larger. So assuming that my A is larger, A is divided by B. Okay, and this is an assumption, not necessary that it should be true in all the cases, because these are two variables chosen, okay, without knowing what they are, arbitrarily chosen. So you have to write the larger number here as a dividend. You should take it, and this divisor is B now. So let us say when you do this division, you get Q as the quotient, you get some R as the remainder. So now A equals B times Q plus r with all the conditions, of course. In the proximity, the conditions you can write, of course. You write here that r is always greater than or equal to 0 and less than or equal to b. Okay, this is how you have written. Now when you write the algorithm, the important point, of course, that should be considered here is, if r is 0, the procedure has come to a halt, is over. Your b is the HCF. But many a time it does happen that this is not 0. So you have to continue the procedure. Then what do you do actually? Like I just bring this b here and I have to continue the procedure. And this procedure continues, okay, and you can write some other s here, and again there is some remainder, you can say r1 or something like that. So this is how it is going about. Okay, when you write the next step, b is equal to r times s plus some r1 you are writing. So you continue this procedure as we have seen in case of numbers until you reach 0 here. And once you reach 0 here, okay, the remainder 0, and whatever you have here, that becomes the HCF. So Euclidean division lemma is used to determine the HCF of two numbers. That is an application of that Euclidean division lemma, and this procedure continues, and this procedure we call it algorithm to determine the HCF of two numbers, and that's it you have got here. So there are two things, of course, which should be focused, and one is Euclidean division lemma. It just gives you the relation between the components of division, and how do we use it to find out the HCF of two integers. Okay, what is the procedure for that? What is the algorithm for that? And another point I mentioned here is that algorithm is derived from the name of an Arab mathematician, Al-Khwarizmi, and his full name is Abu Ja'far Ibn Musa Muhammad Al-Khwarizmi. Okay, now in this topic, real numbers, like we also have a very interesting another property of these integers once again, and let us look at that, and later we can start doing some problems from exercise. Okay, so when you take the next of what the topics you have in this chapter, real numbers, you have a fundamental theorem of arithmetic. Okay, I just write it as fundamental theorem of arithmetic. Fundamental theorem of arithmetic. So this is a very simple one, okay, and we need not bother much. We must have noticed that right from lower classes, but only thing is we just generalize and write it now, nothing more than that. Say you have a number, let's say 6. This 6 is a composite number because this is not a prime number. You call it a composite number. You also should remember that 1 is neither prime nor composite, okay, and we have taken a composite number 6, and this 6, why is it a composite number? It has got some factors other than 1 and itself, okay. You can write this 6 as 6 times 1. Everybody knows that, of course, because 6 comes in its own table and also in the table of 1. But you can write it in some other way also, like you can write this 6 as 2 times 3. Don't say 2 into 3. Into is only the name of the symbol. Better you call it 2 times 3, and that is your 6. So what have you done here? Okay, you should understand, you have factorized this 6 and you got 2 times 3. Okay, having factorized this, there is something more interesting here. These are prime numbers. 2 and 3 here are prime numbers, and therefore this factorization is called prime factorization. Okay, so as I end up here as two prime numbers, so I call this prime factorization. You can write Z here or S, no problem, of course. Prime factorization. Let me take, say, a multiplication and check whether it's a prime factorization or not. Now, I have, let us say, 3 times 4 equals 12 and 12 equals 3 times 4. And can you tell me if there is any difference between these two? Okay, obviously I changed the sides, it doesn't end there. These two are completely different in mathematics. Okay, the first one is called multiplication and the second one is called factorization. Okay, they don't mean the same. They're totally two different procedures altogether. Okay, you have written that 3 times 4 is a product you have written as 12, but this 12 is resolved into its factors 3 times 4. So these two are not different. Never think that this is multiplication and this is factorization. Okay, and they are not one and the same. That should be remembered actually. But when you write 12 as 3 times 4, there is something more to be done to this one. Here 12 is factorized, you got 3 times 4. 3 is a prime number, no problem, but 4 is not. And therefore, this is not prime factorization. A little more has to be done. So what I should rather do here is, this is 3 and this 4 again can be written as 2 times 2. Now all are prime numbers and this is what we mean by prime factorization of 12. Okay, you can't leave it here. So you have factorized, but it's not complete factorization. Something more has to be done. So you have 3 times 2 times 2 when you write. All the factors you have written are prime numbers. You should remember that when you are adding some numbers, okay, and each of them is called a term. When you are multiplying some numbers, each of them is called a factor. So you should know when you call it a term, when you call it a factor. Okay, it does make some difference there. Okay, the terminology. So I take another number like say 10. I take 100. When I take 100, if I write that as 25 times 4, 10 times 10, 20 times 5, it's not complete. Okay, I can say make a beginning, I can write 20 times 5. I did factorization, but it's not prime factorization. Okay, let me further do this. If I write say 2 times 10, this 20 is written as 2 times 10. Even then it is not prime factorization because I still have a 10 here, which can be further factorized. So now what I do is 2 times, this 10 is written as 2 times 5. Of course, this 5 I copy down. Okay, 2 times 2 is 4. 4 times 5 is 20. 20 times 5 is 100. So now 2 and 5 are prime numbers. So my prime factorization is done. So now I can also write this in a different way. 2 because it's 2 times. This is exponent and 5 you have a 2 times and 5 squared. You can write this as 2 squared multiplied by 5 squared. So I want to tell you something. When you multiply these two numbers repeatedly, okay, you can write it as a par. Okay, that you should must be a bit careful. Suppose if you write a par x, okay, is equal to some m when you are writing, this x is called the index. Okay, it's also called exponent. This a is base. But mind you, the whole thing is the par. X is not par. Remember that. So you should know that this is the base and you have an index. How many times you are multiplying this base and the result is par. So it's not, x is the par. X is not. You should understand that m is the par. Let us take a small, like a par and see how exactly you can determine the value of that. Say you have, say 5. 5 is multiplied, let us say 6 times. This is not an easy operation, of course. 5 should be multiplied 6 times. I write 5 times 5 times 5. 6 times I have to multiply. And this is going to be a huge number, of course. 5 times 5 is 25. 25 times 5 is 125, 125 times 5 is 625, 625 times 5 is 3125, and multiplied by 5 is 15,625. That's a huge number. So you should understand that this is the power. When you have this as the base and this as the index, or this can be called exponent as well, and base, exponent, and this is power. Power is not something you have there on the top, of course, it's not that. So base raised to power of index is all the time power, and calculation of power is not that easy, of course, because even if you take say 2 raised to power of say 20 times, if you multiply, you can't imagine that how big the answer can be. I just want to tell you this is 10,48,576. So it ends up as such a huge number, and because just 20 times you are multiplying, but when you add 2 20 times, it is only 40. Okay, if 2 is added to 20 times and there's a repeated addition, and that becomes a multiplication, 20 times 2 of course is 40, but when 2 is multiplied 20 times, it's a huge number. Of course, you can't think of how big it's going to be, 10,48,576. Having understood that, but here we are talking about prime factorization. I just will give you a number like say 200. Okay, and having done this 100, if this is multiplied by 2, I get this 200. So there is only one more 2 here. That's it. So 2 times 3 and 5, so okay, 2 cubed multiplied by 5 squared. Let us understand how this is 2. When it's cubed, of course, you get 8. 2 times 2 is 4, 4 times 2 is 8, and this 5 times 5 raised to the power of 2 is 25. You can say 5 power 2, okay, and 5 raised to the power of 2 is 25. This is 8. This is 25, and that is how you get it. Okay, this is 8 times 25. This is just for verification, and you got your 200 once again. So when you prime factorize 200, you write it as a 2 cube times 5 square. So that is what we mean by prime factorization. Maybe in your lower classes, you did it in a different way. Let me just show you how this was done in lower classes. Okay, it's something like you had 200 here, and you said that this is divisible by 2, and 2 times 100. You can write the remainder here 0. Now not necessary, because this is a factor. You also thinking that whether it's a factor or not, only you are taking factors. So this 100 is divisible by 2. You said you got 50. 2 times 50 is 100, and 50 is again divisible by 2, and you said 25 you are going to get. Now you have to stop here, because 2 is not a factor of this one. You have to check 3 is not a factor. Then you take 5 is a factor 5 times. How did you do this in lower classes? This 200 is 2 is there 3 times and 5 is there 2 times. So you have written that 200 is 2 cubed times 5 squared. So this is how you got your prime factorization. So 200 is the number given to you. You have written it as 2 cubed multiplied by 5 square. So that is how you have written that as a prime factorization. But what is the new thing you are learning here? It is, this is unique. Okay, order may be different. You must have 2 3 times and 5 2 times. That's it. 2 repeats 3 times and 5 repeats 2 times. That can be, different. And therefore, what you are learning here, okay, as the fundamental theorem of arithmetic, is that the prime factorization, whatever you have done, is unique. Okay, only thing is the order might change, because you can write 5 this side, 2 that side, whatever it is. So if you are writing 200, obviously you have 2 3 times and 5 2 times, and this is unique. It can be something different. You don't get any other prime number here, and if you have 5, it must be there, but if it's there 2 times, it must be there. So you can't get a different style of writing this 200. You should ultimately, whosoever does it, it should end up like this. But maybe I can put this 5 this side, 2 that side. That doesn't make much of a difference. Order being immaterial, this 200 can be prime factorized exactly this way. There's nothing more than that. And therefore, the fundamental theorem of arithmetic categorically states that any integer can be prime factorized in a unique way, okay, barring the fact that the order can change. If that can be ignored, because if the order is not straight away taken into consideration, this can be resolved as a product of prime numbers in a unique way, one of its kind. It can be different. You can't make another prime number come here. You can't make, say, if 2 is repeated 3 times, it should be only 3 times. And you can't take out 1, 2 here and all that, like put some other number. You never get this 200. Okay, so this is what we mean by fundamental theorem of arithmetic, and which states that any number, integer for that matter, can be resolved into prime factors in a unique way. Okay, and only one small adjustment that you have to understand, that order may change, but you should have the same number of prime factors of each kind of that, and that is unique. Of course, it's very uniquely it can be prime factorized. Okay, if you have done that, we look at a few problems from the exercise, and let us see how easily we can work out those problems. This chapter, real numbers, has got only two important ideas here. One of them is that Euclidean division lemma, which talks about the relation between the components of division, dividend, divisor, quotient, and the remainder. And the second one, of course, which is rather important, is that the prime factorization in a unique way of any integer, assuming that we don't take the order into consideration. Now let us say I just take a problem here using Euler's division algorithm. Find the HCF of, I am given two numbers, of course. Say one number is 135 and the second number is 225. Okay, and this is an easy proposition, and we use the division method for this one, or HCF method, whatever it is. Like, we have to find out the HCF of these two numbers using the division method. 225 is divided by 135, and 2 times this is 270. You don't have there, it's only 225. Say 1 time. So 135 1 time is 135, and leaving here 90. 5 minus 5, 0, and borrow 10 from here. 12 minus 3 is 9. So as you haven't got the remainder 0, you should continue the procedure. Of course, we have learnt the algorithm to find out the HCF. So this procedure continues. This is R, and you must bring this B here. Okay, and if you go with this 90 table, 90 times 1 is 90, 90 times 2 is 180. You don't have there. So 90 times 1 is 90. And when you subtract, you have 45. Oh my God, still my remainder is not 0. I have to continue further, and I write this 90 here again. And fortunately, 45 times 2 is exact 90, leaving a remainder 0. So I have come to an end. How do I know that I have come to an end? Because this is 0 I got, and my procedure is over, and I applied the algorithm of determining this HCF of two numbers, and this is the HCF. So I can write here that HCF is equal to 45. But if you want to understand, of course, what we exactly mean by this one, 45 times 3 is 135, and 45 times 5 is 225. 45 is the biggest number that goes in both of them. Okay, you also can see 5, but 5 is not the HCF. Why? Because there is another one which is larger than 5. It can be 15 you have there. Okay, so just for your understanding, why is 45? 45 times 3 is the first number, and 45 times 5 is the second number. and that's how we got this 45 as the HCF of the two numbers we are given. And I just do one more small problem here. Use Euclid's division lemma. Show that the square of any positive integer is either of the form 3m and 3m plus 1 for some integer m. Okay. Now, square of a positive integer. That's what is given. My problem here is very simple. Let me say this is my problem number 1. I am with my problem number 2. And you have an integer. Okay, let the number be, say, x. Okay, it's actually an integer. But he is asking me to square it. Okay, and he said if it is squared, it can be either this form or that form. Any square you are considering should be either this form or that form. And he said, no, it can't be that. That's what we are supposed to do. Okay, fine. If I have x here, okay, now it can be as a multiple of 3. It can be as a multiple of 3 plus 1. It can be a multiple of 3 plus 2. And that's it. It can be a multiple of 3 plus 3, it can be, because there are only 3 remainders possible. Any integer here, 0 as the remainder, 1 as the remainder, 2 as the remainder, because the remainder can never be more than 3, because you are dividing it by 3. Okay, you have taken some integer, it should be in one of these 3 forms actually. But the question is not that. He says when this is squared, you don't get all the 3 forms. Oh, he said either this or that, only these 2 forms. That's what we need to do actually. Let us now consider the square of the integer. Consider the square of x. Consider the square of x. So if I take x square, it can be 3m whole square. It can be 3m plus 1 whole square, or it can be 3m plus 2 whole square. It should be in one of these forms actually. Okay, fine. Having done that, here 3m whole square is 9m square. Okay, and 3m plus 1 whole square, this has to be expanded like a plus b whole square. A square plus b 2ab plus b square. This is another method. And this is another one. What is that one? 9m square a square plus 2 into this 2 times 3m 6m, 6m times 2 12m, and later 2 square is 4. So now if I take an integer x which is in these 3 forms, I want to check what happens to x square. It should be in one of these 3 forms actually. But let me consolidate this one. It can be 3 times something, 3 times 3m square. Okay, and let me take this one. If I take 3 as a common factor here, 3 into something, 3 into 3m square plus 2m, of course plus 1. 3 into 3m square is 9m square, 3 into 2m is 6m, there is a 1 left here. Okay, so this form, and you look at the last one, 3 comes as a common factor, 3 times 3m square, this is 4m, 3 times 4m is 12m. I also write 3 times 1, 3 times 1 is 3, but I have 4 here. So I am left with 1. I repeat, 3 times 3m square 9m square, 3 times 4m is 12m, 3 times 1 is a 3, and this is my 4. So this is how my square of any integer can be. What are the different forms I got? It's a 3 multiple plus 1, again 3 multiple plus 1. And therefore, the square of any integer, it can be 3 multiple plus 2. and that's what you should notice. It can be either 3 multiple or 3 multiple plus 1. So finally you can say that if you have the square of a number, an integer, it should be in the form of 3 multiple or 3 multiple plus 1, not 3 multiple plus 2. So as an integer, you have the option of any of the 3, but as the square of the same integer, you have the option of only 2 of them, either 3 multiple or 3 multiple plus 1. That is what you are supposed to notice. Exactly in the same way, okay, he has given, the cube actually, okay, the cube of an integer there. So what you should do, he has given that it can be in the form of 9m or 9m plus 1 or 9m plus 8. So how do we consider this one? You take, say, some y as your integer, and it can be in any of the forms because he is dividing it by 9, of course, 9m, 9m plus 1, 9m plus 2 and so on till 9m plus 8. You take all of them, your integer can be in any of those forms, 9m, 9m plus 1, 9m plus 2, 9m plus 3 and so on, 9m plus 8. But when you cube that y, you don't get in all the forms, it's only limited. And that's what you have to find out. That is another problem, and that is your exercise 1 and 1.1, and I do a few problems from exercise 1.2. okay, and this exercise 1.2 is about prime factorization. I just take a few sums. Okay, my first problem is a very simple one. It's just to prime factorize a number 3825. So this is exercise 1.2, and I have a number 3825, and this must be prime factorized. Okay, as simple as that. So as I look at the number, the last digit is 5, and therefore 5 must be a factor of this one. When I divide this by 5, 5 times 7 is 35, 3, 2, 5 times 6 is 30, 2 and 5, 25, 5, 5 is 25. And once again, I see that there is a 5 at the end in the units place, and you must have 5 as the factor once again. So you have 5 here, 5 ones are 5, 2 and 6, 26, 5 5s are 25, there is 1 remaining, 1 and 5, 15, 5 3s are 15. But I can't divide this 153 by 5. It's not possible, So, but I can look at this number, and if I add 1 plus 5 is 6, 6 plus 3 is 9, a multiple of 3. And therefore, I have a 3 in this one. 3 goes in this one. 3 5s are 15. Bring down 3. 3 1s are 3. Okay, 51. And obviously 51 is of course a composite number. 3 goes in this one, and 3 17s are 51. So I have prime factorized it. What do I have now? My 3825 can be written as 5 2 times, 3 2 times, and 17 1 time. 5 2 times, 3 2 times, and 17. I can write here 1, or I can just leave it. So this is how I have prime factorized. And you should notice that 3, 5, 17, these are all prime numbers. So no further factorization is possible, and we have done this. Now let us understand by taking two numbers what we mean by LCM and what we mean by HCF. Okay, and my numbers here are 510 and 92. So in this question, let me take this as first question. My second question, 510 and 92. And he is asking us to prime factorize this one, and to, then using that, you should find out LCM and HCF. Now I take this 510 and 2 goes in this one 255 times. Now I say 5 goes in this one 51 times, and 3 17 times. It's done. So 510 is, there is a 2, there is a 3, there is a 5 and 17. Order not necessary. There is 1 2, there is 1 3, there is 1 5 and 1 17. Leave it, it's closed. We will take second number, 92. 92, 2 goes in this one, 46 times, and 2 goes in this 46 23 times. 23 is a prime number, so just leave it, it's over. So your 92 can be written as 2 times 2 times 23. 2 times, and there is a 23. Fine. Let me write this here, like my 510 is 23517, 23517, and 92 second number given to me is 2 times 2 times 23. And if you want HCF, it is a single line answer. You need not struggle for that. What is in common? Okay, so it's obvious that there is a 2 which is common, and here you have 3, here you don't have. Maybe here you have 5, you don't have here. There is another 2, but there is no 2 there. And therefore here HCF is just 2. Is the only common factor. You can't have even another 2. Fine, leave it there. Now you want to find out LCM. You write maximum number of times wherever you have that particular prime factor, that you have to note down. Here you have 1, 2, here you have 2 times 2. So you take 2 times 2. The first one. Then you have a 3 here. Though you don't have here, you have to make a note of that. You have a 5 there, you should note it, though you don't have here. You have a 17, you must make a note of that. And 2 times 2 I accommodated here, remember that, of course. Okay, 1 time and 2 times. So 2 times you must write here. What else we have? You have a 23 also, of course. So you write 23 here. So my LCM should have all of them and all of them separately. Like, do I have 2, 3, 5, 17? Yes, 2, 3, 5, 17. And do I have this one? 2, 2, 23. 2, 2, 23. That's it. If you can verify that fact and you have got your LCM here, 2 times 2 is 4, 4 times 3 is 12, 12 times 5 is 60. Okay, 60 times 17 you should take, and that should be multiplied by 23 later. Okay, and this is 1020 because 6 is 17s 102 and this 0, and this should be multiplied by, because still here 60 times 17 I have done, and this should be multiplied by 23. Okay, 23 into 1000, 23,000. 23 times 20 is of course 460. So this is going to be our LCM. So you listen to this particular point, of course, where it should be noticed so carefully. This 510 we have written as the product of prime factors. This 92 we have written as prime factors. If you want HCF, it is very easy. Whatever is common, you should write. I have 2 here, 2 here. Okay, and nothing else is common. 3, 5, 17 I don't have here. I have another 2, but this 2 is not found there, another 2. Only 1, 2 is common. So I just have written HCF is 2. Highest common factor. Done. Come to LCM. You should be able to find all and all these also. How do we do that? If I write, say, there is 1, 2, there are 2 times 2. I have written 2 times 2. There is a 3 copied here. There is a 5 copied here. There is a 17 copied here. Okay, and here you should accommodate this 23 also. And the product I have taken, and I got this 23,460. And there is find LCM and HCF of the following integers by applying the prime factorization method. Of course, there are 3 numbers given, and 3 numbers also you resolve into prime factors, and exactly in the same method you can find out HCF and LCM. It's not a question, it's a very easy one, of course. Then given that HCF of 2 numbers is 9, find the LCM of those 2 numbers. Okay, this is like you are given, okay, HCF you are given. I am taking my third problem. Let's say HCF of 306 and 657. For these two numbers, HCF is given as 9, and LCM of the same two numbers you should find out. Question is that. Okay, so there are two numbers given and you are given the HCF also, and you need to find out LCM. But remember one thing, when you are given two numbers, there is absolutely no need for you to get this 9. You can find out. Okay, when you are given two numbers, you can find out. But he has given with an intention that use this and find out LCM. Okay, he's not asking you find the LCM and HCF both, because half the question is done. Okay, you already have your HCF with you. So here it is, there is a relation. We learned that LCM times HCF is the product of the numbers you are considering. So given this fact, okay, and now I need to find out LCM. I know my HCF is 9 and my first number is 306 and second number is 657. So this is a very simple proposition. My LCM is this 9 comes down to the denominator. That's it. 657 by 9. Okay, and this 9 goes in this one. Okay, 9 times 3 is 27 and 36 is 9 times 4. So this gets cancelled in this one. 20, 30, 9 3 is 27 and 4. So you have a 34 left here and this is 657. And you need to write the product of these two. That's it. 657 multiplied by 34. Okay, and do some simple multiplication, no problem. 4 7s 28, 2 over here 22, 2 2 26, and then you multiply this by 3, 21, 17, 7 1 and 19 here. Okay, then 8 3 7 1 2. So your LCM is 21,738. So how did we do this problem? You are given two numbers and also the HCF of the numbers, and you need to find out the LCM from the relation that LCM times HCF is nothing but the product of the numbers you are given. And there is an interesting problem here. Explain why 7 times 11 times 13 plus 13 and 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5 are composite numbers. Okay, now here 7 times 11 times 13 plus 13, this is what you are given. Okay, this is textbook problem number 6. Don't bother about it. But here, why is this a composite number? Is there any way you can tell that this is a composite number without actually finding out okay, the value or anything? So I do one thing. There are two terms here. This is one term. As long as you have factors, there is only one term. This is another term. Okay, when they two terms, they got something in common, because 13 I am finding at both the places. So if I take 13 as a common factor, I am left with 7 times 11 is 77. I repeat, 13 is found here and here as well. 13 is taken as a common factor. 7 times 11 is 77. And this one is 13 times 1. Okay, this is 13 and 7 times 11 is 77. So this is 13 77s and this is 13 ones. Having done that, if you can take 13 is a common factor, this is 77 and this is 1. And 13 times 78. Okay, and now you can easily say 13 times 78, you got two factors. When you can write a number as a product of two factors, it can never be a prime number. Don't look at the prime numbers here, because this is okay, product of prime numbers, and this is composite, but this is a prime, this is a composite, But mind you, the sum of these two is again a composite number, because I showed that the number is a product of two numbers, 13 times 78. Okay, if you can show something as a product of two numbers, as obviously, like, you need not explain that it is a composite number, not a prime number. Prime number can't be resolved into a product of two factors other than one in itself. Like, there is another question here, and 7 to 1 he is multiplying all the numbers, and there is another 5. Okay, and from 7 to 1 he is multiplying 7, 6, 5, 4, 3, 2, 1, and there is an additional 5. He is telling that it is a composite number. Why? Okay, and let us understand this. I'll take out 5 as a common factor directly, because that makes us sensible here. So I write 5 times. I took out 5 as a common factor. So I write the product of rest of the numbers. 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24, 24 times 6 is 144. Okay, 144 times 7, 1008. Okay, 144 times 7, 144, 7 times 7 fours, 28 plus 2, 7 ones plus 3. Okay, so I have 1008 plus. This is 5 times 1. 5 is written out, so I'm left with 1. So now I have 5 times 1009. So as the number, okay, whatever comes, of course, when you simplify, is written as a product of two factors. So this must be a composite number, because you have written the given number as the product of two factors. That's a composite number. This is my exercise 1.2, and in exercise 1.3, and this is something about rational and irrational numbers. He is asking you to prove that it is irrational. Okay, and there are two problems, of course, I consider in two different varieties, and I prove that they are irrational. You may be given a simple number like root 2 and root 3, root 5, root 7. These are all irrational numbers as long as you do not get a perfect root. But don't say root 9. Root 9 means plus or minus 3. Plus 3 and minus 3 are integers. Therefore, root 9 is not an irrational number. Root 2 is irrational. Root 3, root 5, root 6, root 7, root 8, root 10. Root 11, root 12, root 13, root 14, root 15. But root 16 is again, because it's 4. Root 16 is rational. So my contention is very simple here. He is asking me root 5 is irrational. Okay, and I have to prove it. So we go by the indirect method here. Okay, means he is asking me to prove that it is irrational. Let me suppose that it is rational. What is going to happen? Okay, he is telling that it's irrational. But I make a supposition that what happens if I think it's a rational number. Okay, if it is a rational number, it's only a supposition. Okay, it's not proved actually. Like in neither we have to prove that it's an irrational number. So if possible, if you think that it is a rational number, you should be able to write it in the form of P on Q actually. Like, so let us suppose, this is an assumption. Let us suppose that root 5 is rational. You can't suppose this one. If you have to prove that it is irrational, you can't suppose that it is irrational. You can suppose that it is rational. There is no problem. Let us suppose that root 5 is rational. So root 5 you should be able to write in the form of P on Q. Okay, root 5 can be expressed because you said it's a rational number. Root 5 can be expressed as P on Q, where Q is not equal to 0. P and Q are integers. Okay, now this is our assumption. Not that it's true. Okay, you have to prove that this is absurd. It can't happen, and this is preposterous, like So let's see how it's wrong, how it's an absurd. Now squaring on both sides, squaring on both sides, what have you got? This side you got 5 and this side you got p square on q square. Okay, now this is a very simple one. Only thing is your assumption here p on q is it is in the lowest terms. There is nothing to cancel. Okay, root 5 is a p over q. Okay, in lowest terms because there is nothing to cancel in lowest terms. If possible, we have done. Now here I bring a q from this side from the denominator to the numerator here. So 5 times q is p square over q. One q is brought here. Now look at this statement. Okay, 5 times an integer is an integer here. Okay, this side you have got an integer because 5 it's an integer multiplied by 5 must be an integer, but this side this is a fraction because you said p and q there is nothing in common, you can't cancel anything there is no common factor, and this side you got a rational number, a fraction you got, a rational number. Okay, and you also can call it a fraction. This comparison seems to be meaningless because one side you got an integer and one side you can't cancel anything in p and q, but there is no common factor. So something will be here other than 1, and this is a fraction. So one side you got a fraction and one side you got an integer, and you're saying that these two are equal, and that is not, like a sensible one. And if you, therefore, why this absurd has come? Because your supposition is wrong. You thought that it's a rational number. So if it were to be a rational number, something absurd, you will arrive at here. And therefore, as this is a meaningless statement, check your supposition. You said root 5 is a rational number, if it's possible. And that is wrong. So what is right then? It must be irrational. And here we write like this. Our supposition is this is absurd, which doesn't happen, meaningless, and our supposition is false. What is our supposition? That root 5 is irrational. This is wrong. That's why we got absurd here. And if this is wrong, this is right. Therefore, root 5 is irrational. So you try to understand this, the method we are following here. We are making an assumption which is exactly, the negation of what is given to us, and we go ahead and we find something, of course, which is against the principles of mathematics. Mathematics says that integer can be equal to a fraction. Okay, that can never happen. That is, meaningless. And why this has come? Because we started with a supposition which is incorrect. If our supposition is incorrect, given statement must be correct. So that is the logic we are using here. Okay, I take a case where I have 3 plus 2 root 5 is irrational. 3 plus 2 root 5 is irrational. This is what you are supposed to prove. So how do we go about? If it is possible, let it be rational. Okay, let us suppose that 3 plus 2 root 5 is rational. This is exactly the negation of the given statement. That's what you have to prove. You are thinking that this is true, not that one, and this is true. So let us write now, if it's a rational number, I should be able to write it in the form of P on Q, where it's in the lowest terms, conditions will write it's in the lowest terms, there is nothing in common to cancel. P and Q are integers and denominator can be 0. So you think that the P and Q, two integers, there is nothing in common. Okay, you can't cancel any common factor. Q is not equal to 1 here. This is the condition. If it is a rational number, this should have happened. Now I take this 3 to that side. So 2 times root 5 is equal to P on Q. This 3 is going to that side, minus 3. Okay, and 2 times root 5 is equal to Q is the LCM of both the denominators. I write common denominator. In this Q goes one time, that P is P. This Q, this is an integer here, Q times this 3Q. Okay, so because 3Q by Q is only 3, remember that of course, because 3Q by Q, P by Q is anyway here. So if you look at this one, this is absurd. Okay, why this is absurd? This doesn't happen. This side you got an irrational number because root is there, irrational number, and this side P and Q are integers. You got integer by integer form. So this side it is a rational number. So you can't equate them like it. No chance. So if you think this is right, this must happen where you have an irrational number on one side and a rational number on another side. You can't equate them. You can't say both of them can be equal. No chance. And therefore it's an absurd. Because this is an absurd, our supposition is false. And this is our supposition. This is not correct. Therefore this is correct. Okay. So our supposition is false. And therefore given statement is true. Given statement is true. Okay, so in all the cases, of course, the method we have used is that whatever you have to prove, exactly the opposite of this one, opposite of that, we say it's true. And we go ahead. And somewhere you arrive at, a contradiction, something which is against each other, against the principles of mathematics. And why did this come? It's an absurd. That doesn't happen. It is inadmissible. We can't consider this in mathematics. But why does this come? So this scenario has arisen because we started with a wrong proposition. And therefore, because this is wrong, what we supposed, the given statement must be true. Okay, that is the procedure we follow here. Okay, and I have a similar problem, but I have an irrational number in the denominator. Say it is 1 over root 2. Okay, and it's easy for me to resolve this one. I need not this. What I would rather do is that, and this is a very simple one. I try to rationalize the denominator. When you are given a number which is irrational, you can't rationalize it because given number is irrational. How can that become rational? Okay, not possible. But I can do one thing. I can rationalize this part. Means the denominator can be rationalized. Naturally, the irrational part shifts to the numerator. So when I am given this one, I multiply numerator and denominator by root 2. So root 2 times 1 is root 2 and root 2 times root 2 is a 2. Okay, try to understand in this number, denominator is irrational. The whole number is irrational. Only change you have made to this and you can convert this as this one. Here what happened, denominator is rational, however, numerator is irrational and therefore this also is irrational. This is irrational, this is also irrational. Okay, fine, leaving that there, if you want to prove that this is irrational, you can straight away start assuming that you can write it in the form of P over Q. So let us write this is irrational number. That's what you are supposed to prove it actually. Okay, and you have written it like this. Don't bother about it. Let us write 1 over root 2 is rational. How can you write like this? If possible, let us think like this. He is telling irrational, but we don't agree with that. Let us say it's rational. What would happen? Let us consider, of course. We go ahead. Now, 1 over root 2 can be written in the form of P on Q, all the conditions. Lowest terms, P on Q, no nothing to cancel. P and Q are integers and Q is not equal to 0. So you should be able to write this in the form of P on Q because you are thinking that this is a rational number. And now let us write squaring on both sides. Squaring on both sides, 1 over 2, 1 ones are 1, root 2 times root 2 is 2, is equal to P square times Q square. If this is the case, okay, you bring Q square times 1, Q square, 2 times P square, 2 times P square. This extends a little further. Must be careful. Q square times 1 is Q square. 2 times P square is this one. Okay, then Q square is a 2 multiple because this is an integer. P square itself is an integer. 2 times that integer is an even number. Q square is even. Q square is even. If Q square is even, because it's a 2 multiple, Q must be even. Because even number only when you square, you get an even number. Q is even. Okay, and now this is a simple one, like Q is even, okay, Q square is even, and it tells you that P square is even. Okay, so P square is even and P is even. It's an implication, of course. P is even. And then P on Q is not in the lowest terms because you said P and Q, there is nothing to cancel. It's in the lowest terms. And therefore, P by Q is not in lowest terms. That's what happened actually. Like lowest terms, you can cancel 2 because both are even numbers. Like how P square is even, I just resolve here. Q is even, let Q is equal to 2m because it's an even number. So Q square is 4m square and Q square is 2p square. Okay, 2p square is Q square. So Q square is 2p square and you cancel 2 here. P square is 2 times m square, where m is an integer, and I found that P square is an even number for 2 times something. P square is even, P is even. So P is even and Q is even. So you can cancel 2 in both of them, and therefore they are not in the lowest terms as you assumed, and therefore this is an irrational number. Which one? 1 on root 2 is an irrational number. Okay, fine. This is exercise 1.3. Okay, and we have the last exercise 1.4. Okay, and I do few more sums here, and there we are. Here in exercise 1.4, you are given some fractions and you have to find out whether they give you a non-terminating and repeating decimals or terminating, as simple as possible. Let us work out, say, take a simple fraction like 17 on 8. Now, first check if you can cancel anything in both numerator and denominator, if there is a common factor. No, you don't have. So, I keep my numerator as it is. I don't want to disturb it, because whether it's a terminating or non-terminating, it is determined by only the denominator. I prime factorize this one. So, I get 2 times 2 times 2. If that can be understood, you have here something interesting. If you have only 2's and 5's here in the denominator, and that is going to, somehow you can convert this into 10, 100, 1000 and so on, because if you have 2, you can multiply it by 5. So by multiplying it with some number, you can make it, like a 10, 100, 1000 and so on. And therefore, this is going to give you a terminating decimal. It stops somewhere. You get terminating decimal. Okay, I want to tell you what I mean by it. 17 is divided by 8. Okay, and 8 times 2 is 16. 1 decimal, and you put a 0 here. 8 times 1 is 8. 2 and 0. 8 times 2 is 16. 8 times 5 is 40. 0. So when you do this, you got a remainder 0. It stopped. It is over. And therefore, this is a terminating decimal. There is nothing to move ahead. Okay, nothing. It won't go beyond that. And therefore, it's a terminating decimal. But I take a fraction, something like, say, I'll just check if this can be 64 on 455. So, assuming that there is nothing to cancel, because these are all 2's you have in 64, because here you don't have. I write 64 without disturbing that numerator, and this I write as 5 times 91. 5 times 91. 91 is 7 times 30. I prime factorize the denominator. 5, 91 times, 7, 13 times. So 5, 7, 13 I have. My observation is a very, very simple one. I can have 5 no problem. I can have 2's no problem. But I can't have 7 and 13. If you have any factor other than 2 and 5, your conclusion can be it's a non-terminating one. You never go and get a 0 remainder here. So this is easily a non-terminating one. Non-terminating decimal fraction it is going to give you. Non-terminating decimal number. And understand the logic here. When you prime factorize the denominator, if you have 2's and 5's, no matter how many times you have it, no problem. That's going to leave with a terminating decimal. But when you look at the denominator, there is a 5 which is allowed. 5's and 2's are allowed. But you can't have any other prime number there in the denominator, and that immediately turns out to be a non-terminating decimal number. Okay, that's what you should be remembering, of course, because what is the advantage of these 2's and 5's? If you have 2, you can supply a 5 there, make it a 10. If you have 5 there, you can supply a 2, make it 10. So somehow in the denominator, you can get numbers like 1 followed by some zeros, tens, hundreds, thousands, and so on, which is not possible when you have 7 and 13 like other prime numbers. Okay, that is exercise 1.4, and that finishes our first unit, real numbers. Thank you so much.